Hi, thanks everyone for coming today. So it is my pleasure to introduce Marie Kawakatsu, who's a PhD candidate in the program in Applied and Computational Mathematics at Princeton University. In her research as a mathematical biologist, she uses tools from evolutionary game theory, dynamical systems, and network science to explore mathematical and computational models of collective and emergent behavior in social systems. And I'm very excited that we're going to hear one of those applications today. So Marie, take it away.
Thank you, Alice. Let me see, let me move the, okay. Great. Yeah, thank you, Alice, so much for the introduction and also the invitation. I'm really excited to talk to you today about some recent work that I've done with Phil Chodrow, Nicole Eichmeyer, and Dan Larimore. Before I get started on that, though, one thing I've really enjoyed about this seminar series is that we've been able to get to know the presenters, how the presenters think about, how they approach network science and from what kinds of backgrounds a little bit. So I'm going to follow their cue and introduce myself a little bit. As Alice mentioned, I'm a PhD student in applied math, but I studied physics and sociology for my bachelor's, which is where I became interested in using mathematical models to capture different kinds of social phenomena. It was the first time that I was introduced to that idea. But once I got to Princeton, though, I learned that a lot of mathematical and theoretical biologists, particularly ecologists, are really, thinking about questions of collective behavior, which were the questions that I was interested in. So during the past couple of years, I've been borrowing tools and ideas from applied math, theoretical biology, and a little bit of sociology to mainly think about how different kinds of heterogeneity, so ranging from individual attributes to population structures, how those kinds of heterogeneities shape and also are shaped by different kinds of collective behavior and social systems. And I think about this across scales ranging from ant colonies to human societies, where I think more about networks and also game theoretic interactions. So you can imagine that, when I attended this 2019 workshop on complex networks in Quebec last year, I was very excited to meet people who were thinking about the commonalities among aggression in parakeets, messaging behavior in online dating, and then finally faculty hiring patterns in academia. These seem fairly different from each other, but it turns out that we can think of them all as endorsement networks with hierarchical structures. So I was really excited to learn about this. And sorry, I see that there's a chat. Oh, thanks, Alice. So what do I mean by that? Let's first think about parakeets. Here I'm showing you a group of monk parakeets, which is a species that's known for its highly social and also communal nesting behavior. But they can get quite aggressive towards one another as they compete for resources and things like that. And Liz Hobson at University of Cincinnati has done some really fascinating work on this aggressive behavior. So in this setting, an endorsement is based on a fight. Individual I is thought to implicitly endorse individual J if I loses a fight to J. So that means that J is stronger, right? So the loser is endorsing the winner. Hobson and colleagues determined this ranking of individuals based on these kinds of endorsements. And then they found that this ranking can capture an important behavioral pattern, namely that parakeets, individual parakeets, tend to aggress against those not necessarily at the top of the social ladder, to entirely take over the ranking, but rather they tend to aggress against those who are nearby in rank. Another example where we find hierarchical endorsement networks is online dating. In a 2018 paper, Elizabeth Brooke and Mark Newman, both I believe at Michigan, analyzed data from an online dating service, they don't name it in the paper, but across 4 large cities in the United States. So in this case, an endorsement of individual J by I meant that individual I initiated a message to J, which implied that I found J desirable in some way or form, right? When they ranked individuals according to this measure, they found a really pronounced hierarchy among the users. And on average, individuals tended to message those that are 25% more desirable than themselves. So again, not necessarily someone who is, considered desirable by everyone, but someone who was, I guess, sort of within the reach, so to speak, which is somewhat of a puzzling result, I think. But then they went into the data and analyzed the sending and receiving messages or behaviors. What they found here, so here at the top 2 panels are showing the probability distribution of sending messages, and then the likelihood of receiving replies, both as a function of what they call the desirability gap. So that's the difference between the desirability of the recipient and the sender. They found that while both men and women tended to message those with positive desirability gaps, meaning those that are more desirable than themselves, they're also much less likely to get replies, as we can see in the decreasing line here. Right, so these factors combined explain perhaps the observed behavior that individuals tend to message those that are like a little bit above their desirability level. And finally, a third example, and perhaps the most striking example for many of us in academia at the moment, is the faculty hiring patterns. The example that I'm showing here on the left is a network of computer science departments in the United States, taken from this 2015 paper by Aaron Clausett and colleagues, including Dan Larimore. Each gray band represents an academic institution and then each arc going from a band to band represents a flow of PhDs from those who got a PhD from one and then went on to become faculty at the other. So the colors of the edges represent the aggregate direction of the hiring movement. For instance, a blue edge from one school to another means that the flow of PhDs between them was in the direction of decreasing hierarchy. And in fact, the authors found that almost 90% of hiring movement actually goes down the hierarchy. And 18 PhD granting institutions account for half of CS faculty in the entire country, which is, I think we all kind of knew this intuitively, right? But it's really striking to see it quantified as a hierarchical network. And as you can imagine, these are just a few examples of endorsement networks with persistent hierarchies. Now, given the fact that these are everywhere and they have like real consequences for parakeets and also for us, we might naturally ask, okay, what are the mechanisms that are generating them? It turns out that people have been thinking about this for quite some time. And the main mechanism that's invoked to explain the emergence of hierarchy in general, though there hasn't been as much work done on networks, is called the winner effect. So this is the idea that winners are more likely to win in the future and losers are more likely to lose in the future. This kind of positive reinforcement has been shown to produce persistent hierarchies in different models. Now, but when it comes to explaining the mechanism behind this positive reinforcement, a lot of the previous work has commonly resorted to the idea of what's called the intrinsic strength. So this is the idea that, when you're in a fight and once you win, something intrinsic or internal about you changes. And as a result, you become stronger, more likely to win, etc. Now, this could be true, for example, in animals who are fighting against each other, perhaps their hormonal state changes. But we actually think this is not necessarily the case in all the cases, all the scenarios that we want to capture. An example that Phil came up with, which I think is particularly relevant for our current time, is, so consider, for example, a prestigious political candidate, I don't know, let's say Bernie Sanders, deciding to end his campaign and then endorsing Joe Biden. Now, the endorsement doesn't suddenly make Joe Biden more fit or less fit for presidency, right? Instead, Sanders' prestige somehow adds to Joe Biden's status through the act of endorsing. So this is the notion of transitive prestige. And as you can see, this lends itself very naturally to thinking in terms of networks. In particular, adaptive networks would be a natural approach. I'm sure many of you have heard of adaptive networks, especially in this audience, but they're a class of models in which node states and edges both evolve, co-evolve. And I think I've heard it described as, dynamics on and of networks combined. The main challenge here, though, is that adaptive network models are actually often hard to analyze and also, or analyze analytically at least, and also to fit to data. So in this project, we wanted to try to connect these two circles. And specifically, we asked these questions. So in a hierarchical in an endorsement network, can a hierarchy spontaneously emerge from an egalitarian state due to this sort of prestige-seeking behavior? And then what do we actually mean by social rank or prestige? And how does that definition of social rank influence network dynamics? And then finally, we wanted to see if we could use empirical data from real social systems to infer the generative mechanisms that are at actually work in these social networks. So in the remainder of the talk, we'll introduce an intuitive adaptive network model of hierarchy that answers these questions. And I'm going to highlight 3 key features throughout the talk. First, it is analytically tractable, and we can describe a sharp transition from an egalitarian state to a hierarchical state. Second, the model is flexible in that it can accommodate a range of ranking functions, score functions, which are, as I said, different definitions of social rank. And finally, our model supports inference. Time-varying network models don't always have tractable likelihood functions, but our model does, and this allows us to use maximum likelihood approach to fit the model to data. Okay. So here's how our model works. At each time t, we have a network A, where the nodes are individuals and the edges are weighted endorsements up to that time step. So for instance, the link from this pink node or salmon pink node to the yellow node means that this pink node endorsed the yellow node in a previous time step. And each node is given a real valued score that reflects their position on this hierarchy, this line. Now we're still at time t. We then make an integer number m new endorsements, and then collect them in this new endorsement matrix delta. So in this example here, there's a single new endorsement made by node I towards node j. After these endorsements are made, we update the network as a weighted sum of the old network A and the new endorsement delta. So here the key parameter is lambda, which we call the memory parameter. And this parameter modulates the relative importance of the new and old links. So a smaller value of lambda means that there's more weight placed on new links, whereas a larger value of lambda means that older links are remembered for a long time. We repeat this procedure over time, and then we try to analyze the long-term behavior of the model. Now, to complete this model, though, we need 2 ingredients to know precisely how the scores determine the new endorsements, right? And that's really where the crux of this model is. So the first ingredient is the score function, which assigns a score I to each node at time t. In other words, the score function, again, is the mathematical definition of social rank. Now, in principle, any function that assigns a real valued ranking to the nodes can be used here. So our model is very flexible in that sense, but here in the paper, we focus on 3 that are A, mathematically tractable, and have important applications. So how do we define social rank? One natural way is to say, okay, how many times has a node been endorsed by others? In terms of the graph, we can think of this as how many incoming edges are there to a given node. So this is reflected in the root degree score function, where the score of a node is the square root of its in degree. Now, you might be thinking, well, that seems a little simplistic. We can be a little bit more complex. And the next step would be to say, okay, how many times has a node been endorsed? And also by whom? This is, you might connect this to the notion of transitive prestige that I mentioned a few slides ago. And to formalize this, we chose two established algorithms, PageRank and SpringRank. PageRank, as many of you probably know, is the algorithm by Brin Page that was originally used by Google to rank websites. And then SpringRank, in contrast, is a model that's inspired by physical springs, thinking about the network as consisting of nodes that are connected by springs, and somehow you're trying to resolve the conflicts using principles, energy principles. Okay. So these score functions determine the scores. And then now scores in turn determine the new endorsements. Now, okay, intuitively, whether I endorse someone could depend on A, whether they're highly ranked or not, right? Or as we saw in the parakeet and online dating examples, perhaps maybe how close my rank is to theirs, that could also matter. And we want to formalize these intuitions into our model. So to do this, we apply a random utility model, which is a standard in discrete choice literature. So in our case, we pick a random node I to make an endorsement. And then this node I will then choose some node J with a probability that's proportional to this exponentiated utility here, which comes from the random utility theory with a particular noise function. And then the utility function is given by this expression here on the right. And then we repeat that process m times, and then collect all the endorsements into the delta matrix. I want to highlight two parameters in the utility function. So here, beta 1 captures one of the intuitions that I mentioned a few seconds ago. So this one corresponds to preference for prestige. In other words, node J is more likely or less likely to be picked if it has a higher score. And then beta 1 represents what we call preference for proximity, which basically means that, is J more likely or less likely to be picked if it has a score that's close to the one that's deciding who to endorse. Okay, so now we have collected all the endorsements in this delta matrix. We can put it back to the update equation here, and then we've come full circle. So before I go into the results, I want to give a quick summary of the model because I know there are lots of parts to this model. So at time t, we have a network A. And then the first step is to compute the scores using the score function, root degree, spring rank, or page rank. Then we make m new endorsements according to the random utility model with the utility function that I just described before. And then finally, we update the network as a weighted sum of the old network and the new endorsements. So we simulated this model to explore its dynamics in different parameter regimes. In the next couple of slides, I'm going to focus on the limit of long memory, meaning the lambda parameter is very close to 1, because it shows, we think, the most interesting behaviors, and also it gives us analytical tractability. I'm going to show 3 simulation runs here with the spring rank score. So the vertical axis shows what we call ranks. I won't go into the mathematical definition here, but you can think of it as basically the likelihood that a given node will receive the next endorsement. So a higher rank means that node will be very likely to receive a next endorsement in the next round. And then the horizontal axis shows time steps. So when the preference for prestige beta 1 was relatively low, the system led to a more or less egalitarian outcome where all the nodes, I should say there are 8 nodes in this particular simulation, but all 8 nodes received more or less the same rank. In contrast, when we increased the prestige preference to 3, we saw a hierarchy emerge. By that, we mean that a minority of nodes, in this case, the 3 nodes here, received a majority of the endorsements. Now, turning on the preference for proximity, beta 2, had a smoothing effect, but it didn't affect the fact that there was a hierarchy. So this makes intuitive sense because a larger absolute value of beta 2 means that, or negative value of beta 2 means that the interactions are more likely to be among individuals with similar ranks, leading to fewer, jumps in rank up or down. So having seen these different patterns, we wanted to see what we could capture analytically. So to do this, we analyzed the model dynamics in expectation. That is, we turned the original stochastic model into a deterministic one by taking the average in colloquial terms. And we found that the 2 behaviors that I showed you before, egalitarianism and hierarchy, are part of a much bigger, more interesting picture. So the bifurcation diagram that I'm showing here shows the expected long-term behavior of the system as a function of preference or preference for prestige on the horizontal axis. It's a little complicated, but the darker branches show the stable equilibria according to our analytical analysis. The lighter ones are unstable. And then the blue circles represent the average of stochastic simulations, which we wanted to test against the analytical results. So as we saw before, when beta 1 is low, the system will be egalitarian in the long term. All nodes have the same rank, right? However, as we increase beta 1 and cross approximately 2, we see that a hierarchical structure emerges. And then it continues growing in variance until we get to a very large value of beta 1. And it turns out that similar transitions are
crazy.
Sorry? Oh, sorry. Not sure what that was, but and it turns out that for the other score functions as well, we see similar critical transitions. And the main theorem of our paper is that we can actually derive analytical expressions for where this transition occurs in this long memory limit. So the transition, I mean, is where the the egalitarian equilibrium becomes unstable, giving rise to a hierarchical state. Interestingly, beta 2, which is the preference for proximity, doesn't affect the location of this transition.
Mary, can I ask a clarifying question at this point?
Yeah, go ahead.
So I know bifurcation diagrams from when I studied them, but in those cases, each branch in a bifurcation diagram described the state of a system. So if you had something like that, it would mean that for some value of your parameter, there's only one way that your system can behave, and then at beta equal to like some threshold, it splits up, and in your simulations, you would see your system behave one way or the other way corresponding to the different branches. But in your case, those are ranks, right? So rather than learning something that the system can be in many different states, it means that the nodes can be in many different ranks, and therefore you have a hierarchy for large enough beta to, is that what I'm seeing here?
If I understood your question correctly, so let's see, let's take this C panel for a second. So perhaps this is a more complicated one. Yeah, well, let's see. So in this case, let's take some value like 7.5, right, for beta. You're right that it's a little bit confusing because there are multiple branches for each beta representing the different node states in a given state. So for example, if we set beta 1 to 7.5, then we would expect to see a bunch of nodes that are at this low rank level, in addition to a few, and I'm not sure how many exactly, but at this highly ranked. Actually, in fact, it should be 1 because the sum of the ranks should be 1. So we would expect to see basically 1 highly ranked node and a bunch of lowly ranked node. If that makes sense.
Okay, okay. Thanks.
Does that help? Yeah.
Yes.
But thanks for the question. Great. Oh, interesting. That was not supposed to happen. But yeah, that's okay. So given that we understand the qualitative behavior of the model, we can ask, okay, how can I actually use the model to qualitatively or quantitatively analyze the hierarchies in this system? I'll briefly explain what we did using one of our case studies. So we studied data on hiring patterns among math PhDs between 1960 and 2000, all at American institutions. And the data were derived from the Math Genealogy Project. So here, the nodes are different universities, and an edge from University I to J means that a mathematician who received their degree from University J supervised one or more degree or PhD theses at I. So this is basically a proxy for University I hiring a graduate from J. So that basically means that University I, endorsed graduates of J as being of good quality. So here's what the data look like. Here we're showing the place, what we call the placement share for each year. So that's the fraction of placements made by graduates of a particular institution. And the highlighted ones are, I believe, more or less the top 8 ranked here. And then because our model has a tractable likelihood function, we used maximum likelihood approach to infer the parameters of the model by fitting the model to data using the different functions. So here we have root degree, page rank, and spring rank. And here's what we found. So we found that the estimated value of beta 1 was greater than 0 for, oh, and I should mention, in addition to the math PhD data, we explored 3 other data sets, 2 of which were about parakeets, and one was about a fraternity, basically a friendship network in a fraternity. So if you're interested in that, check out our preprint. But we found that in all 4 data sets, beta 1 was estimated to be greater than 0, and beta 2 was estimated to be less than 0. Now, if we recall from the form of the utility function, these values suggest that, in fact, preferences for both prestige and rank proximity are likely at work in these systems. Furthermore, the likelihoods give us a way to compare which functions are actually giving the best fit, right? It's really hard to visually see the different trajectories and see which ones give the best fit, but this is a statistically principled way of doing so. And interestingly, in the case of math PhD, we found that root degree performed best. Now, if you recall, root degree is the one that doesn't incorporate transitive prestige. So this suggests that in this particular data set, a school that places more candidates has a higher score, regardless of where the candidates land. Now, of course, we need to do a more comprehensive comparison of different score functions and then do a deeper dive into this to fully uncover the mechanisms that are operating in this math PhD data. But the point I want to emphasize is that our model does offer a statistically principled way of understanding dynamic hierarchical data. Great. So, to summarize, we've introduced an intuitive generative model of social hierarchy that hopefully I've convinced you that it's flexible, analytically tractable, and it also supports inference. Now, there are a few directions for future work that we're thinking about. So depending on the system, first of all, or domain of interest, the particular form of utility functions or score functions that we picked might not be the most appropriate. So there's definitely a lot of room to explore there, although our general results we hope will hold. Also, so far we've assumed that basically all the individuals have the same preferences for prestige and proximity. But even in the case of math PhD, perhaps institutions that are more highly ranked have different kinds of interests compared to those that are more in the lower ranks. So it'd be interesting and also really important to think about what happens when their preferences are different. And then finally, I know there's a growing interest both here in this audience and also the broader network science community in higher order interactions. So as a natural extension of our model, we're thinking about defining hierarchy and studying generative mechanisms there. Now, this is usually where I end this talk, but given the interest of the seminar series to showcase women in network science, I decided to add an epilogue about citation diversity statements. So I'm sure some of you have heard of citation diversity statements. This comes primarily from recent work in the neuroscience community, where they've really highlighted that there's a strong gender imbalance in reference lists. So in this 2020 paper, Jordan Dworkin, Danny Bassett, and colleagues, they analyzed citation patterns in top 5 neuroscience journals. And they found, sadly, but perhaps expectedly, that papers with men as both first and last authors were cited 11.6% more often than expected. And by that, they mean relative to the ratio in the existing literature. Now, in contrast, papers with either woman first author or last author were cited less often than expected. I do want to note here that the way they categorized the names was basically they took the names of the author, the first and last authors, and then determined the probability that that would have been a name that would be assigned to a baby assigned male or female at birth. So it's a very, they have the details in the paper, obviously, and they also go into depth about who's driving this dynamic. So I would definitely encourage you to check out this paper if you're interested in this kind of stuff. But at the end of this paper, as one mitigation tool, they propose what's called a citation diversity statement. So these are statements that quantify the equitability of a reference list by listing, among other things, the gender balance of the authors that are cited. So for example, the ratio of male versus non-male first authors or last authors. I really like the definition that this recent paper by, I think, Perry Zern and others, where they say that the statement is a simple statement of fact and a consciousness raising tool. I think that captures the ethos of this practice. So we thought this was a great idea. So we decided to write our own statement. Because our reference list wasn't terribly long, we decided to manually code the names of the first and last authors. This was based on either personal knowledge, pronoun usage online, or first name. We analyzed this table and then wrote a statement. You can read the full statement on our preprint, but the summary is that of all the references that we cited, about 3 out of 10 had a first author with a non-male name, and about 1 out of 8 had a last author with a non-male name. And here we're typically in the papers that we cited or the fields that we cited, the first author is the lead author, the last author is the senior author. And then of all the references with 2 or more authors, 38%, or about 4 out of 10, had either a non-male first author or a non-male last author, or both. So at least 1 non-male author in those positions. Now, there are certainly limitations to our approach. Names or pronouns may not be indicative of gender identity, and there's certainly some subjectivity when we do this kind of manual coding. But I think it just helps, at least it helped us reflect on, what does our reference list look like? So we put up the preprint and then we submitted the manuscript. And since then we've learned a couple of things. So our statement has certainly a lot of interesting dialogue on this topic of gender representation, both among our colleagues as well as with reviewers. There does seem